Va bene, e adesso faccio lo sharing. Va bene, adesso dovreste vedere il mio desktop. Allora, quindi diciamo, riprendiamo da dove abbiamo lasciato ieri. Ieri vi ricordo, nella seconda parte della lezione, abbiamo introdotto il modello statico a quark, che fu appunto proposto nel 1964 sostanzialmente da Gell-Mann e Neumann, per dare una risposta a quelle regolarità che si osservavano quando tutti quanti questi nuovi hadroni, che furono scoperti in tempi brevissimi, nell'arco di pochi anni, si capì che potevano essere sistemati in modo coerente in uno spazio in cui abbiamo sostanzialmente da un lato la terza componente dell'isospin e dall'altro l'ipercarica. Okay? Quindi queste regolarità, mi ricordo come abbiamo detto ieri, hanno fatto supporre che in realtà tutti questi hadroni appena scoperti non fossero oggetti elementari, particelle puntiformi, ma che queste regolarità fossero lo specchio di una struttura interna, di una organizzazione interna all'interno di questi oggetti. Okay? Di qui appunto l'ipotesi di quark che abbiamo discusso, e in particolare abbiamo visto che il modello a quark si basa su una nuova simmetria, che è la simmetria di Flavor, SU3, che ha 8 generatori, che sono le 8 matrici di Gell-Mann, e in particolare abbiamo visto che utilizzando la teoria di gruppi, nell'ambito di questa simmetria globale, è possibile classificare in modo opportuno i mesoni, che abbiamo già trattato ieri, e i barioni, che tratteremo oggi. Okay? Allora, andiamo quindi avanti adesso sulla parte dei barioni. So, baryons, as we know, are bound states of 3 quarks, and the lightest, so the low-lying baryons, involve only up, down, and strange quarks. And so in total, we have 27 flavor combinations, and all of those have vanishing orbital angular momentum. In this sense, they are the so-called low-lying states, or the ground states, if you want, of the baryon spectrum. Now, their multiplet structure can be obtained much like in the same way we did already for the mesons, by first considering the multiplet structure for the combination of 2 quarks in this case, and then by adding the third quark. So we proceed now in 2 steps. So the combination now of 2 SU3 quark triplets, one here and one there, results in group theory into a symmetric sextet of states and an antisymmetric triplet of states. Okay. Now our task, we want to build up baryons, so we have to add one more quark triplet. So 3 quark triplet, and when we combine these, the result is that we have to multiply this system of a sextet plus a triplet with another quark triplet. Okay, so the result will be the sextet times combined with the triplet plus the triplet combined with the triplet, and this is reported here. And let's now treat them separately. So when you combine now the sextet with the triplet, the triplet, you obtain now a decuplet of totally symmetric states plus an octet of mixed symmetry states. Let me remind you that mixed symmetry means that these objects are symmetric under exchange of only the first 2 quarks. Okay. There is no specific symmetry when you change the first and the third, or the second and the third. When, on the other hand, you combine now the 2 remaining quark triplet, you obtain another octet, in this case of mixed asymmetry states. Okay, so these states are asymmetric for exchange of the first 2 quarks, plus a totally antisymmetric singlet. So this is the overall picture, the overall spectrum of low-lying baryons that you obtain in the framework of SU3 flavor symmetry. And in the language of group 3, the result is the following. So you combine 3 quark triplets, and you would obtain at the end a fully symmetric decuplet, a mixed symmetry octet, a mixed asymmetry octuplet, and a totally antisymmetric singlet. So let's now go a little bit more into detail here. In general, the wave function of baryons is obtained by combining the flavor wave function component together with the spatial component, the spin component, and also the color component that we will discuss next in the course. So overall, the total wave function of a baryon is given by the combination of these four components, okay? And by requiring that the overall wave function, so this guy here, must be antisymmetric under the exchange of any two quarks. Now, let's be more specific here. So for the case where the flavor wave function describes equal particle, so either up, 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 or down, 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 or strange, strange, strange baryons, then this requirement here is a direct consequence of the Fermi-Dirac statistics, okay, trivial. The reason, however, why this should also apply to the more general case with different quark flavors, such as up-down strange, arise from the Pauli exclusion principle, so still from the Fermi-Dirac statistics, but in combination with the SU3 symmetry. And the proof of this, which is provided in quantum field theory and is based on the algebra of the creation operators, is quite complicated and goes beyond the scope of this course. Okay, so we will not prove this. Now, a few words about the low-lying baryons. The special wave function is symmetric for low-lying state baryons, of course, because L is equal to 0, and the symmetry of the spatial wave function, as we have seen, is -1 to the L, so this gives us always a +1. What about now the color, this last complicated term here? Now, the color wave function of baryons is always antisymmetric, and the reason we will learn, of course, in the chapter of QCD, so a few weeks from now. Now, but we want the total wave function to be antisymmetric, okay? So low-lying state baryons can only be formed from totally symmetric combination of the two remaining components, which is the spin and the flavor, under exchange of any two quarks, okay? So we want this to be antisymmetric. We know that the spatial is symmetric, we know that the color is antisymmetric, so the combination of the remaining two must be symmetric, okay? Now, now we have also to combine the spins of three quarks, okay? So 3 1/2 spins. And as we know, these are the results. These I think we already discussed in the past. So when you combine now 3 spin doublets, you obtain a quadruplet, which is totally symmetric, and 2 doublets, which are one mixed symmetry and the other mixed antisymmetry. Okay. So now we have to combine together the flavor component of the wave function and one of those spin component of the wave function in order, okay, to provide the total component, and require this combination of the two must be symmetric. So how can we do this? There are essentially only 2 ways, okay? So the symmetric combination of spin and flavor wave function can be obtained in those 2 ways. The first one, we combine a symmetric flavor decuplet with the symmetric spin 3/2 state. So we combine this symmetric spin state together with, for the flavor, this guy here, which is totally symmetric. So when you combine symmetric with symmetric, you obtain, of course, something which is symmetric. And this combination describes, indeed, the baryons of the decuplet with spin 3/2. The other possibility is now to mix the mixed symmetry, mixed asymmetry flavor octet together with the mixed symmetry and mixed asymmetry spin states. Okay, and doing this way, you would obtain now the baryons of the octet with spin 1/2. The third possibility is ruled out because it is not possible to construct again a totally symmetric flavor times spin wave function from the antisymmetric flavor singlet. Let me go back here. So we cannot use now this singlet, this antisymmetric singlet, to combine to create with baryon wave function, because there is not a corresponding totally antisymmetric spin state for 3 spin 1/2 particles. So you cannot combine these in the proper way with the proper spin component. So the only 2 ways to obtain baryon wave function, okay, are those here. The first one, combination, works for actually produce the wave function of the baryons of the decuplet with spin 3/2, and the other one, the baryons of the octet with spin 1/2. Let's now make these more clear on the board. Okay. So again, so this is now slide 1. So this is the total wave function of the hadron, and we have indeed 4 contributions. Okay, the spatial times the flavor times the spin times the color. Okay, so we know that the spatial component is symmetric. We know that the color wave function must be antisymmetric. We want the total wave function to be antisymmetric, and so as a result, we need the combination of the flavor and spin to be symmetric. Now, when we combine the symmetric flavor state with the symmetric spin state, which is the quadruplet with spin 3/2, then one obtains a symmetric combined flavor times spin wave function, and this corresponds to our decuplet. So Jp equal to 3/2 plus. Okay. The other possibility that I was already showing in the slide, okay, is now to combine the mixed symmetry and the mixed asymmetry. Okay, so in this case, you need to construct the following combination. So 1 over square root of 2, and then we have for the flavor mixed symmetry combined with the spin mixed symmetry plus flavor mixed asymmetry combined with the spin mixed asymmetry, and this gives us a symmetric, again, flavor times spin wave function, and this corresponds to the octet. Sorry, so is Jp equal to 1/2 plus, and these are the octet states. All right. Now, in analogy to the spin states that I showed before in the slide, we can also define in much like the same way the mixed symmetry and mixed asymmetry flavor states. So the one we're using now here. Okay, so this one here and this one there. So for the mixed symmetry, these are defined in this way. So isospin 1/2, third component minus 1/2. And these are built in this way: 1 over square root of 6, 2 down, down, up, minus up, down, down, minus down, up, down. And the other one is I equal 1/2, but now third component is positive. And it is 1 over square root of 6, 2 up, up, down, minus up, down, up, minus down, up, up. Whereas for the mixed asymmetry case, we're going to have I 1/2, I3 minus 1/2, defined as 1 over square root of 2 u dd minus d u d. And for the other one, with the positive third component, we're going to have 1 over square root of 2 u du minus d u u. Okay. So these mixed symmetry, mixed asymmetry flavor wave functions components are the analogous of those for the spin that I've shown in the slide. Okay. You can obtain one from the other by exchanging the upward arrow with a up quark and the downward arrow with a down quark. Okay. Now, let's now use all these, in particular the second prescription here, okay, to build up a wave function of an octet baryon. In particular, we will do for the case of the proton, the spin-up proton in particular, okay? So the spin-up proton wave function is, of course, a notable example of a quark model wave function for an octet baryon. So let me go now to a new page. Page 2. Okay. And the same, of course, applies to the neutron. So in general, for the proton or the neutron, okay, when we combine now spin and flavor, this is done, given by 1 square root of 2 psi spin mixed symmetry times psi flavor mixed symmetry plus psi spin mixed symmetry times psi flavor mixed symmetry, and overall this will be symmetric as we want. So let's now start with the case of spin-up proton. Wave function. So we have, first of all, to combine the two mixed symmetry spin and flavor wave function. So we start from the first piece, mixed symmetry, spin time, mixed symmetry flavor. And now we use the expression of this wave function that I just showed you before. So 1 over square root of 6 for the spin is 2 up, up, down, minus up, down, up, minus down, up, up. And this has to be combined with the corresponding flavor mixed symmetry wave function, that is 2 up, up, down, minus up, down, up, minus down, up, up. So let's combine them. So you put the coefficient outside, and then you have 4 u up, d down, minus 2 u up, d up, u down, minus 2 d up, u up, u down, minus 2 u up, u down, d up, plus u up, d down, u up, plus d up, u down, u up, minus twice u down, u up, d up, plus u down, d up, u up, plus d down, u up, u up. And now this piece here is still symmetric for the exchange of one with the second only. Now let's do the same exercise for the mixed asymmetry terms. So spin mixed asymmetry times flavor mixed asymmetry. In this case, the combination is 1 over square root of 2. For the spin, we have up, up, minus down, up, combined with 1 over square root of 2, u du minus d u. And so this is going to be 1/2 u up, d down, u up, minus d up, u down, u up, minus u down, d up, u up, plus d down, u up, u up. Ok, vi lascio qualche minuto per copiare, ditemi quando siete tutti pronti così cambio pagina.
Professore?
Sì?
Una domanda. come mai lei sta sempre scrivendo prima up e poi la relativa freccia? Cioè, è una convenzione oppure proprio un... bisogna
Beh, sto
sempre spiegare in modo da-
combinando.
Non è equivalente, per esempio, a scrivere tutti in sequenza, tipo freccia su, U di U, per esempio?
Beh, io qua sto facendo una funzione d'onda combinata, sto mettendo insieme la componente di spin e quella di flavor, quindi di fatto sto, come dire, sto assegnando a ciascun flavor il proprio spin.
Ok. Ok, ora ho capito.
Prof,
Ok.
scusi, anche ho una cosa da chiedere. Forse ero rimasto indietro a copiare, ma nell'ultima riga, cioè, ci
Sì,
sono due frecce per alcuni quark oppure si è sbagliato a scrivere?
due frecce per alcuni quark. L'ultima riga la rileggo. Ah, perché, sì, perché ho spostato il foglio, quindi si è scritto, scusate.
Ah, ok.
Allora, la leggo a voce, la leggo a voce l'ultima riga. Allora, U up, D down, U up, meno, D up, U down, U up, meno, U down, D up, U up, più D down, U up, U up.
Ok, grazie.
Ok? C'è qualcuno che deve ancora copiare?
Io ci sono.
No, io
ci
no.
sono.
Ah, ok,
Cioè,
dimmi.
nel senso, non devo copiare.
Fatto?
Non devi copiare. Siete tutti a posto?
Sì.
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 Ok, allora andiamo avanti. Adesso dobbiamo ovviamente combinare, sommare questi due contributi e sostituirli nella riga 1, ok? Dove li stiamo sommando. Allora, cambiamo pagina. Ok. Allora, quindi questa è la pagina 3. Quindi psi spin flavor combined. Let's now adapt everything. So we substitute everything in the first expression. So it's 1 over square root of 2. And now we have U up, D down, minus 1/3 U up, D up, U down, minus 1/3 D up, U up, U down, minus 1/3 U up, U down, D up, plus 1/6 U up, D down, U up. Okay, then plus 1/6 D up, U down, U up, minus 1/3 U down, U up, D up, plus 1/6 U down, D up, U up, plus 1/6 D down, U up, U up, plus 1/2 U up, D down, U up, minus 1/2 D up, U down, U up, minus 1/2 U down, D up, U up, plus 1/2 D down, U up, U up.
Su, giù. Su.
Adesso possiamo noi sommare i pezzi, diciamo, dello stesso tipo. Quindi per esempio abbiamo questo un testo up di down up che si va a sommare con questo un mezzo up di down up. Poi abbiamo questo qui un sesto, lo faccio con 2 righe, un sesto di up u down u up che va a sommarsi con questo un mezzo meno un mezzo di up u down u up. Poi abbiamo questo qui, lo faccio con 3 righe, un sesto u down di up u down che va a sommarsi con questo qui. E poi l'ultimo è questo pezzo qui, lo faccio con 4 righe, 1, 2, 3, 4, va a sommarsi con questo qui, 1, 2, 3 e 4. Quindi adesso facendo queste somme troviamo 1 over square root of 2, 2/3, u up d down minus 1/3, u up d up u down minus 1/3, d up u down minus 1/3, u up u down d up plus 2/3 u up d down u up minus 1/3 u down u up d up minus 1/3 u down d up u up plus 2/3 d down u up u up. Abbiamo finito, eh? Adesso sì, dimmi.
Prima abbiamo scritto le combinazioni delle funzioni d'onda come delle psi, dello spin o del flavor. Sì. Per completezza, sono le stesse funzioni di cui abbiamo scritto all'inizio, che prima erano quindi delle phi e delle xi?
Sì, assolutamente, ho solo cambiato il nome, ma è la stessa cosa. Sì. Ok. Allora, a questo punto abbiamo tutti gli ingredienti, semplicemente riordiniamoli in modo opportuno e troveremo a questo punto la funzione d'onda del protone con spin up. So, psi p up spin times flavor 1 over square root of 18, and now you have 2 u up d down minus u up u down d up minus u down u up d up plus 2 u up d down u up minus u up d up u down minus u down d up u up plus 2 d down u up minus d up u down minus d up u down u up. And it is our final result. So this is the combined spin and flavor wave function for a proton with spin up in the framework of the quark model. Okay, so this wave function in fact is given by a combination of all these possible quark and spin configurations. And all this is to be sure that the total wave function, when we also combine this with the color component and the spatial component, will be antisymmetric for exchange of any two pairs of quarks. Ok? Ci siete tutti? C'è qualcuno che deve ancora copiare?
Posto.
Va bene. E allora adesso riprendiamo questa cosa sulle slide. Ok, siamo sulla slide 5, quindi qui trovate adesso il risultato che abbiamo ottenuto con tutti i vari passaggi. In particolare qui è espresso in modo più compatto, perché vedete, per ottenere quella completa che vi ho dato poco fa, vi basta fare tutte le permutazioni cicliche di questi termini, di questo primo termine che avete qui. Okay? Troverete esattamente tutti i 9 termini che vi ho detto prima, che vi ho dato prima. Okay, this was for the proton. What about now the spin-up neutron? Of course, now we don't have to repeat this exercise, this very boring exercise, actually. You just need to exploit the isospin symmetry, so you can obtain the neutron wave function from the proton wave function by just exchanging up with down quarks, okay? So if you change up with down, you obtain the correct wave function for the neutron up. Again, this is only the combined flavor and spin components. And the wave function of all the other hadrons of the octet can be worked out in a similar way. Ok? Now, adesso veniamo a una domanda che mi aveva rivolto uno di voi un paio di lezioni fa, cioè riguardo alla scoperta della omega meno. Ne parliamo in questa slide. So when the quark model was proposed by Gell-Mann and Zweig, and Neumann also, in 1964, there was an empty spot in the baryon decuplet. So all these baryons were already discovered at the time at the accelerators, but there was something missing here. A baryon in particular with vanishing isospin, hypercharge -2, and strangeness -3. So with containing 3 quarks, of course, 3 strange quarks. And the mass also, this was also predicted to be of the order of 1670 MeV. Okay, so this was missing. And the particle and its mass was then predicted by the quark model before this particle was eventually discovered. Okay. Now, the discovered came essentially in the same year, so 1964, at BNL, so at Brookhaven, close to New York. And in a bubble chamber, they found this complicated event topology. Okay. This was a hydrogen bubble chamber hit by a Kaun beam. So you see here. So this is the figure. This is now to clarify the figure, and this is what happened in practice in the decay. So you have a K- hitting a proton of the bubble chamber. In the collision, 3 objects are created, an omega minus here with a very short track, a K0, which is here, which is neutral and so does not leave any signal into the bubble chamber, and a K plus, which is this guy here, this charged track up to here. Then the omega minus, that was this missing particle here, was found to decay into a pi minus here, and some neutral and so unobserved baryon, which further decay, which is the psi 0, which further decay into 2 other neutral hadrons. One was the pi 0, which in turn decays into 2 gamma, one here and one there, and each of these 2 gamma decay into an electron-positron pair. And the other was a lambda 0, which is here, also neutral, so also not observed, which eventually decays into a proton and a pion. Okay, so this is the full decay chain that was trapped by this photograph in the bubble chamber. Okay. And this was the first evidence for the existence of this omega minus baryon. Okay, so the discovery of this new particle with a mass very, very close to the predicted one, where the prediction was simply based by the quark model, of course, And with the desired quantum numbers, so vanishing, it is an isospin singlet, so vanishing isospin, and then hypercharge -2 and strange -3 was then discovered. And the discovery of this particle, which was predicted by the model, was of course gave of course a very strong support to the quark model. Okay. Now, what about now all other baryons in the decuplet? So the 10 totally symmetric flavor combination in the baryon decuplet are the following. So you see we have an isospin quadruplet, the delta minus, 0, plus, and plus plus, which occupy this row here in the plane. Then we have an isospin triplet, which are the sigma star. One of those we have discussed yesterday in a problem, if you remember, which now occupy now this row here at 0 hypercharge. Then we have two double strange baryon, the xi plus, the xi star minus and xi star 0, which sits here. And finally, we have this omega minus, which is a strange baryon. Okay, a very strange baryon, I would say, which is of course a singlet of isospin, so it stays here, and which has the corresponding value. Now, to remember the value we see in the table of the hypercharge. Now, let's have the full picture now of the light baryons. So experimentally, one observes the JP3 half plus baryon decuplet, which is this one here, and one of the two octets, in particular the one with JP 1 half plus. And all these objects are all low-lying states, so they all come with vanishing orbital angular momentum. And so this observation, in fact, was a striking agreement, was again a success of the model. Okay, this was in striking agreement with the prediction of the quark model. Okay, so in the octet we now have two isospin doublets, the neutron and proton, as we know. This is the first isospin doublet that we did. Then we have another one, which are the two double strands xi, and then we have the sigma, which are an isospin triplet, and then we have the lambda, which is an isospin singlet here. Now, why the parity is positive? So we have seen plus here and plus there. This is trivial because when you calculate the parity of a baryon, as we've done already, we have -1 to the total orbital angular momentum, and then you multiply by the intrinsic parity of the quarks, which are all positive. So you get a +1 sign. The total orbital angular momentum is 0 because we are dealing with low-lying states. So overall, the parity for all these objects is positive. Now, what about the other octet and the singlet? So the quark model foresees the existence of one decuplet, two octets, and one singlet, if you remember. Now, the known observation of the other octet and of the singlet is now a consequence of the QCD dynamics, which restricts the physical case to only those with an antisymmetric color wave function. So in other words, the QCD, which was developed, of course, afterwards, put some more constraints on the quark model, okay? And the constraint, as I was already mentioning before, is that the baryon wave function must be, the color component of the baryon wave function must be antisymmetric. And once you apply this requirement, then at the end, this results in the non-observation of the remaining octet and singlet, okay? So everything is perfectly explained in the framework of the QCD. Now, this table summarizes the main properties of the octet baryons, okay? So we have the strangeness here, the isospin, the symbol of the baryon, the mass, the decay time, the main decay modes, and the interaction that regulates this decay, okay? So first of all, we have the proton and the neutron, okay? We don't know if the proton is stable. We discussed this yesterday. It might be unstable, but with a very, very, very large decay time, at least larger than 10 to the 34 seconds, years, sorry. Then we know that a free neutron is unstable and decays weakly into a proton plus an electron and a neutrino. This is the beta decay that we will be studying next. Then we have the isospin singlet, the lambda. Okay, this is the mass. And all these guys here, also the heavier one, decay weakly with the only exception of the sigma 0, which decays electromagnetically into a lambda and a photon. Okay. And if you consider also the decay time here, you see that apart from that, which is typical of electromagnetic interaction, all the other are much, much longer, so typical of the weak interaction. This is now the table for the decuplet baryons. Okay, so we have the 4 deltas, which constitute an isospin quadruplet. This is the mass, and all these guys decay up to here, decay strongly, so with very, very short decay time. Okay, the only baryon that decays weakly, so it cannot decay strongly, is the omega minus, and the reason is that the omega minus is the lightest baryon with 3 strange quark. So it cannot decay into an even lighter baryon with having 3 strange quark, because it is the lightest. And so to decay, he needs to violate strangeness. And this is only possible through weak decays, through the weak interaction. Okay. Now, so far we have considered only the low-lying state, so with vanishing orbital angular momentum. However, of course, hundreds of mesonic and baryonic excited states have been discovered with non-zero orbital angular momentum. Okay, so with L1, 2, 3, and etc. And also these baryons can be organized in successive SU3 multiplets and can in fact be considered as excited states of the low-lying states. So the low-lying states are, if you want, the ground state of the baryons. Okay. Now, let's now discuss again the problem of the masses, much like we did yesterday for the mesons. Okay, so here you see now the masses of the baryons of the octet and the masses of the baryons of the decuplet. What we can say from this number? So while particles lying on the horizontal lines, so isospin multiplets, so these 2, these 3, these 2, or these 4, these 3, these 2, etc., have almost the same mass, and this is a consequence of isospin symmetry, of course. The masses in consecutive horizontal lines differ by something like 130, 150 MeV. Okay, so if you move from here to there, from there to here, to there, etc., you get a jump of order 130, 150 MeV, as you can see from these values here. Okay. Now, these mass differences are due to the relatively high mass of the strange quark, as we've seen yesterday, with respect to the up and down, which are only a few MeV. And clearly, the mass hierarchy that you see here reflects the number of strange quarks in the state. Okay, so the omega, for instance, is the heaviest because it has 3 strange quarks. This has only 2, this has only 1, etc. Now, this is 0. The delta is 0. Now, if, again, the SU3 symmetry were exact, then one would expect that the mass of all the baryons within the octet and within the decuplet would be the same. Okay. However, as we see already from this table, this is not the case clearly. And similar to meson, then the difference between the masses of the octet and those of the decuplet, okay, only derive from the different spin. So we have 1/2 spin here and 3/2 spin there. Okay, and so as much as we've seen yesterday, also the difference between the masses of the decuplets and the corresponding masses of the octet can be explained in terms of the chromomagnetic interactions. Okay, we will see now here in this slide. So for baryons, one has to sum up now the spin-spin interaction over all quark pairs. So now we have 3 quarks, so we have to consider all 3 combinations. Okay, this is the way we sum them. So this we calculate in the usual way, as we've seen yesterday, through the expectation value. And so what you obtain here is -3,4 for the sum of these expectation values for the case of the octet baryons, and +3,4 for the case of the decuplet baryons. Okay, where we use now, of course, this notation here. So when we put now everything together, we obtain now the corresponding phenomenological formula for the baryon mass, for the low-lying state baryon mass. Okay, so now in this case we have to sum up the mass of the 3 constituent quarks. Then we have a parameter A prime, okay, which is again proportional to the coupling constant of the strong interaction and to the probability to find each pair of quarks at the same place. Okay, so at relative distance 0. And then we have the 3 contribution from the spin-spin interactions, divided by the corresponding mass products. Now, in order to obtain a good agreement with the measured values, okay, one has to use in this formula these values for the constituent quark masses, and this value for the A prime parameter. Now, if you compare these values from those that we used yesterday for calculating the mass of the mesons, they are different. Okay, these are higher in general. And this should not be a surprise, however, because the QCD environment within a baryon is clearly different than the QCD environment within a meson. Okay, and so it should not be a surprise that, of course, these constituent quark masses that take into account the dressing due to the gluons and to the quark-antiquark virtual quark-antiquark pair can be different between mesons and baryons. Okay. So let's see now in this table how the calculated values of the mass compare with the experimental values. So the theoretical means calculated with this phenomenological formula, and here you see now the experimental values. This is for the octet, and this is for the decuplet. Okay. So again, despite the simplicity of this formula and the simplicity of the quark model, the static quark model itself, the agreement is pretty good. Okay. So again, the quark model seems to work quite good. Okay. Yeah. So the phenomenological model provides a very good prediction also for the low-lying baryon masses. Ok, facciamo una pausa, vediamo che ore sono. Sì, dai, facciamo una pausa di 10 minuti, oggi è un po' più breve la lezione. Ricominciamo alle 12:05 e poi andiamo sull'ultimo argomento di oggi, che è il momento magnetico dei barioni.
Ok. Un'altra domanda sulla notazione, prof.
Sì, dimmi.
Ok, nel grafico di destra, nella tabella di destra, lo star sta per
Sì.
il fatto che il momento angolare è 1 in più.
Allora, lo star dove lo trovo? Ah, sì, sì, sì. Sì, è per distinguere dei torti, chiaramente dei simboli diversi per non fare confusione. Quindi, siccome adesso qua sei sul decupletto, hai 3 medi di spin, usi la star per distinguere.
Ok.
Sì.
Grazie.
Niente. Vabbè, riprendiamo alle 12:05 allora. Ok, ci siete ragazzi? Mi sentite?
Io sì, ci sono.
Ok. Allora, riprendiamo adesso, andiamo sull'ultima parte della lezione, quindi passiamo alle slide. Ok, vediamo adesso un'altra applicazione del modello a quark e una sua previsione anche per quelli che sono, in questo caso, i momenti magnetici del protone e dei barioni in generale. So, if nucleons were point-like Dirac fermions, the magnetic moment would be exactly given in terms of the nuclear magneton. So we start from the general formula. G is the Dirac-magnetic ratio, if you remember. This is the electric charge, the mass of the proton, electric charge of the proton, and this is the spin operator. Now, if it were indeed a point like Dirac fermion, G is equal to 2, so these two cancel here. The charge of the proton is the same of the electron, of course, in absolute value. And then you can also write down the spin operator in terms of the Pauli matrices multiplied by h bar divided by 2. And this guy here is indeed the so-called nuclear magneton. Okay, so the Dirac the magnetic moment of the proton, for instance, would be, if it were a Dirac particle, exactly in magnitude equal to the nuclear magneton. Now, we know that the measured magnetic moments of proton and neutron differ substantially from this prediction. So the one from the proton is 2.792 times the nuclear magneton, and the one for the neutron is minus 1.913 times to the nuclear magneton. Clearly, protons and neutrons are not, obviously, are not point-like Dirac fermions, and their anomalous magnetic moment, which arise from their composite natures in terms of quarks, can be explained in the framework of the quark model in terms of the magnetic moments of the individual quarks. So let's see now how this machinery works. Now, quarks are now Dirac fermions, so we can apply the standard expression for the Dirac magnetic moment, so G is equal to 2. And so we can write down here the operators for the total magnetic moment, and what we need here is along some quantization direction, so along the Z, okay? So we can relate these to the spin direction along the Z. And QQ is the charge, electric charge of the quark in terms of the electron electric charge, and this is the mass of the quark, the constituent mass, clearly. Now, let's move to the board. Quindi questa è la pagina 4. So let me write down again the operator for the Z component of the magnetic moment for a quark of charge QQ, mass MQ, and spin SZ. Okay, in particular for the spin up U quark, we know that the eigenvalue of the spin is plus h bar half. And so we can write down the expectation value of the magnetic moment for the U quark with the spin up. This is an arrow, okay, pointing up. So this expectation value we can write as U up, then our operator, and then U up. Here we can substitute our expression for the magnetic moment operator. So this is the electric charge of the up quark in terms of electron, then we have the mass of the up quark, and then here we have the expectation value of the spin along Z, that is h bar half. So the charge of the up quark is plus 2/3 of the electron charge. Then we have still the mass of the up quark, and then the expectation value for the spin operator is h bar divided by 2. And so this we can write as plus 2/3. We can multiply and divide by the mass of the proton. So is mass of the proton divided by mass of the U quark. And then here we have E h bar 2, and again the mass of the proton that cancels. But then in this way, we put explicit the nuclear magneton, mu n. So we can write the expectation value of the magnetic moment for an up quark with spin up as plus 2/3 mass of the proton, mass of the up quark in units of the nuclear magneton. What about the down quark? It is exactly the same. The only difference is clearly the electric charge. So let's calculate now the expectation value of the magnetic moment for a down quark with spin up. So this would be d up mu z d up. That is now the charge of the down quark, the mass of the down quark, and then we have d up sz d up. Now the charge of the down quark, as you know, is minus 1/3 in terms of the electron charge. Then we have the mass of the down quark and h bar divided by 2. Again, we multiply and divide by the mass of the proton. So this is minus mass of the proton divided by 3 times the mass of the down quark. And then we make explicit again the nuclear magneton. So overall, the expectation value for the magnetic moment of the down quark with the spin up is minus mass of the proton divided by 3 times the mass of the down quark in units of the nuclear magneton. Obviously, if you now consider the case of spin down, then the eigenvalue will be Sz minus h bar half. And so by proceeding in the same way, we would obtain the expectation value for the up quark with the spin down as minus 2/3 mass of the proton, mass of the up quark, and in units of the nuclear magneton. And similarly, the expectation value for the down quark with spin down will be now positive. So m proton, 3 times mass of the down quark in units of the nuclear magneton. Now, let me also tell you that if we assume with a good approximation that the mass of the up quark is the same as the mass of the down quark, then by comparing the two, you find that the expectation value for the magnetic moment of the up quark is approximately minus twice that of the down quark in this approximation. Okay. So let's come back now to the slide. And we are here. Okay. Now, let's construct now the expectation value of the magnetic moment for a proton with spin up in the framework of the quark model. So in the quark model, clearly the total magnetic moment of a baryon in general is given by the vector sum of the magnetic moments of the 3 constituent quarks. Okay, so for a baryon, we have to sum up these 3 vectors for the quark 1, quark 2, and quark 3. Therefore, the expectation value of the magnetic moment for a spin-up proton, which is our, let's say, baseline example, can be written in this way. So mu p is equal to, this is the wave function of the proton, the one that we derived before, okay, with the 9 terms. And so we have to calculate this matrix element, essentially, where in between we have the z component of the magnetic moment operator. Okay, and this we can split as the sum of the one for the up quark, and the down quark. We know that the proton is an up-down baryon state. Okay. Now, consider that you have to put this wave function here and there, and you have to make all the product. So this will be a mess. Okay. So the matrix element would contain something like 81 terms. Okay, come from to these cross products. However, fortunately, due to the orthogonality of the quark flavor and spin states, all the non-diagonal terms are vanishing. So the terms where this ket is different from this bra, they are all equal to 0. Okay. So at the end, we only have 9 pure terms, which are the diagonal terms. And let's now write them down in the board. Ok, pagina 5. Okay, so let's now write down only the surviving terms, which are the 9 diagonal terms. So the magnetic moment of the proton, the expectation value, is meant. Now, when you take into account the proton wave function for the spin up, it is 4 divided by 18, and then we have u up, d down, mu z, u up, d down. This is the first term. Then we have plus 1 divided by 18, u up, u down, d up, mu z, u up, u down, d up, plus 1 divided by 18, u down, u up, d up, mu z, u down, u up, d up, plus 4 divided by 18, u up, d down, u up, d down, u up, plus 1 over 18, u up, d up, u down, mu z, u up, d up, u down, plus 1 over 18, u down, d up, u up, mu z, u down, d up, u up. Siamo a 6, altri 3, plus 4, 18, d down, u up, mu z, d down, u up, plus 1 over 18, d up, u down, mu z, d up, u down, and the last one, plus 1 over 18, d up, u down, u up, mu z, d up, u down, mu up, u up. Voilà. Vi do qualche minuto per copiare. Okay, now we make use of the eigenvalue equation. Okay, so mu z over u up returns plus mu u up. Similarly, mu z acting on u down returns minus mu u down. And then we have the same for the down quark. So mu z down up is equal to plus mu d up, and mu z d down is equal to minus mu d down. And so now using these eigenvalues, we can write down the single individual expectation values. So the u up mu z u up is going to be equal to the corresponding eigenvalue mu u. Then we have the u down mu z u down is equal to minus mu u, and same for the down quarks. So down up mu z down up is given plus mu down, and d down mu z d down is equal to minus mu d. Ci siete tutti? C'è qualcuno che sta ancora copiando?
Un secondo.
Sì? Dimmi te quando è finito.
Prego.
Ok, siete tutti a posto? Ok.
Sì.
Cambiamo pagina. Adesso andiamo a sostituire ovviamente questi valori di aspettazione dentro questa espressione più generale. Ok, allora questa adesso è la pagina 6. So the expectation value for the proton magnetic moment then reduced to 4 divided by 18, and then we have mu u plus mu u minus mu d plus 1 over 18, mu u minus mu u plus mu d plus 1 over 18 minus mu u plus mu u plus mu d plus 4 divided by 18 mu u minus mu d plus mu u plus 1 over 18 mu u plus mu d minus mu u plus 1 over 18 minus mu u plus mu d plus mu u plus 4 divided by 18 minus mu d plus mu u plus mu u plus 118 mu d plus mu u minus mu u plus 1 over 18 mu d minus mu u plus mu u. Allora, qui possiamo semplificare un po' di roba, quindi questo va via con questo, 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 questo va via con questo. Quindi quello che risulta è 4 divided by 18, 2 mu u minus mu d plus 1 over 18 mu d plus 1 over 18 mu d plus 4 over 18 2 mu u minus mu d plus 1 over 18 mu d plus 1 over 18 mu d plus 4 divided by 18 2 mu u minus mu d plus 1 over 18 mu d plus 1 over 18 mu d. Va bene? E adesso vi fate voi, diciamo, ci sono proprio 2 passaggi di algebra elementare, da terza media, da seconda media forse, e alla fine di tutto, ok, quando vi fate questi passaggi, troverete come risultato finale μp uguale 4 terzi mu u meno 1 terzo mu d. Quindi questo è il valore di aspettazione del momento magnetico del protone in termini dei momenti magnetici del quark up e down, trattati come particelle di Dirac.
Ok.
Bene. Ci siete tutti? Allora, a questo punto possiamo tornare sulla slide. And of course, we can obtain the neutron magnetic moment in the same way just by exploiting the isospin symmetry, so by exchanging U with D, okay? And then the expression remains the same. Now, we can also use the approximate relation that I showed you before, which is valid when one assumes that the mass of the up and the down quark are approximately the same. So mu U equal to minus twice mu D. And then one can compute the prediction for the ratio between the magnetic moment of the neutron and the magnetic moment of the proton within the flavor symmetry, so within the quark model, essentially. Okay. So in the numerator you have the result for the neutron. In the numerator the result for the proton. Then you apply this approximation here. Okay. And overall you obtain a ratio of minus 2/3. And then you can compare this prediction with the experimental value. Okay. Which is pretty close, so in a good qualitative agreement. So again, another, let's say, success of the model. But we can do even more with the quark model. Let's now indeed try to make the prediction for the proton and neutron anomalous magnetic moments that we have seen before in the slide. So the best agreement between the quark model prediction and the measured values of the magnetic moments for the low-lying state baryons is obtained using these specific values of the constituent quark masses. Okay. Now, if you come back to what we derived before, so the expectation value for the magnetic moment of the up quark is given this term in units of the nuclear magneton. And when you substitute now the mass of the proton and the mass of the up quark that you see here, you obtain a plus 1.85 in units of the nuclear magneton. And the same for the down. This is minus 1/3. Okay, you substitute the mass of the proton, you substitute now this mass of the down quark, constituent mass, and you obtain minus 0.97 in units of the nuclear magneton. Okay, and now we go back to the proton and the neutron. Okay, so with these values, the up and down quark magnetic moment, one can exactly reproduce the observed values of the proton and neutron magnetic moment. So we substitute these into the relation that we just derived on the whiteboard. We put these numbers here and there, and we obtain exactly plus 2.79 nuclear magnetons for the proton and minus 1.91 nuclear magnetons for the neutron. Okay, and this is indeed another impressive success of the quark model. Okay, so with very simple arguments, we are completely forgetting about QCD, about gluons, about internal dynamics. Nonetheless, the model, which is a static model, in fact, is able to reproduce precisely the measured anomalous magnetic moments of the proton and the neutron. What about the other baryons? Okay, so here we have a bunch of baryons. And here you can compare the experimental value and the expected value from the quark model. Okay, so these are the measurement with uncertainties, and these are the prediction by the model. Okay, so these are the two relations that we derived for the proton and the neutron, but of course you can derive similar relation for the other baryons. Okay, and the agreement is pretty good. Okay, let me now, is not always perfect, of course, but for sure it works perfectly for the proton and the neutron. Let me now focus only on the lambda zero, because it is a very special case. So the lambda zero baryon is an up-down strange baryon and contains an up and a down quark whose spins are coupled to zero. So so up and down quark in the lambda zero are in a spin singlet state. And so they contribute neither to the spin nor to the magnetic moment of the baryon, because if spin is zero, then also the magnetic moment is zero. And therefore, both the spin and the magnetic moment of the lambda zero baryon are determined solely by the remaining quark, which is the S quark. So these two up and down contribute zero to the spin and magnetic moment. So overall, the magnetic moment of the whole baryon corresponds to the magnetic moment of the single strange quark. Okay, which is given by this simple relation in terms of the nuclear magneton, and this is the value that you obtain. Okay, which is in fact in a very, very nice agreement with the experimental value, if you use this value for the constituent mass for the strange quark. So let's now stay still on this point here and solve a problem on the lambda 0 baryon, okay, just to emphasize what I've just told you. So the text is the following. Calculate the magnetic moment of the lambda baryon in the framework of the quark model using the following values for the constituent quark masses. Okay, so mu is equal to md, 336 MeV, and then the strange quark weights 509 MeV. So we move back to the whiteboard. Questa è la pagina 7. E questo è il problem 5.9. Okay. So differently to the other baryons of the octet, the lambda 0 is an isospin singlet, as we have seen. So the isospin is 0, and third component is also 0, of course. And therefore, the flavor wave function of the up-down quark pair must be antisymmetric. So if we write down the flavor wave function for the up and down quark only, okay, this must be a singlet. So antisymmetric, ud minus du. If you swap d with u, you obtain a minus sign. In this sense, it is completely antisymmetric. So as a consequence, in order to have now a symmetric combined flavor times spin wave function, that is, if you remember what we need in order to have a fully antisymmetric baryon wave function, also the spin wave function must be antisymmetric. And so the spins of the up and down quark must form a spin singlet. So for the spin part, still for the up and down quark, these stay in a s equals 0 singlet state, square root of 2. So up, down, minus, down, up. Okay. And therefore, as I was mentioning before, the up and the down quarks contribute neither to the spin nor to the magnetic moment of the lambda baryon. Okay. And therefore, the spin and the magnetic moment of the lambda baryon must depend only on the remaining s quark. So let's first write down the combined flavor and spin wave function for the up-down pair. Okay, so this is, let's now combine those two. Okay, so the way we have done already for the case of the proton, this is much simpler now. So it's 1 of square root of 2 up, down, minus, down, up, ud minus du, okay, for the flavor part. And then we have 1 of square root of 2 up, down, minus, down, up for the spin component. And so we can now combine both and obtain u up d down minus u down d up minus d up u down plus d down u up. So this is the combined flavor times spin wave function component, but only for the up and the down quarks. Okay. Now you want to construct the wave function of the lambda 0 baryon, so we have to add the third quark, which is a strange quark, and this we can do trivially. So the lambda 0, for instance, for a spin up, is obtained by just combining this wave function with the corresponding one for the spin up. So 1/2 u up d down, I'm just copying this, u down d up minus d up u down plus d down u up, now combined with the s up quark state. And so overall, this is 1/2 u up d down s up minus d up u down s up minus u down s up, sorry, d up s up plus d down u up s up. And this is the wave function of the lambda baryon. So once we have this, we can now calculate the expectation value of the magnetic moment for the lambda 0 in the same way we did for the proton. So this is now the lambda 0 up Then we have the Z component of the magnetic moment operator, and then we have the same state here. Again, all the non-diagonal terms are vanishing, so we consider only the 4 diagonal terms. So this is going to be 1/4 U up, D down, S up, mu Z, U up, D down, S up, plus D up, U down, S up, mu Z, D up, U down, S up, plus U down, D up, S up, mu Z, U down, D up, S up, plus D down, U up, S up, mu Z, D down, U up, S up. Ok, ditemi quando ci siete tutti, così cambio pagina.
Ok.
Ok, ci sono?
Ci sono.
Ok, abbiamo quasi finito. Allora, ok, cambiamo pagina. Allora, questa è la pagina 8. Okay, now we proceed as we did before for the case of the proton. So again, mu lambda is equal to 1/4. Then we have mu up minus mu down plus mu s. We now take the expectation values, plus mu down minus mu up plus mu s plus minus mu u plus mu d plus mu s plus minus mu d plus mu u plus mu s close. Also here we can simplify. Possiamo semplificare un po' di roba, quindi questa, 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 questa. E come vedete rimangono soltanto i termini che dipendono dal quark strange. So this is 1/4, 4 times the expectation value of the strange quark magnetic moment, that is exactly mu s, that is minus 1/3 mp divided by ms in units of the nuclear magneton, that is minus 1/3 938 MeV divided by the 509 MeV, which is the constituent quark mass of the strange quark, in unit of the nuclear magneton. And the numerical result is minus 0.614 mu n. And again, this is in extremely good agreement with the experimental value, which is lambda mu exp equal to minus 0.613 plus or minus 0.004.
Così? Il fattore 1/3, da dove è comparso? Ah, ok, sì.
Ok.
No, mi sono
Ok, va bene. Va bene, la lezione finisce qui. Se avete domande, dubbi, altrimenti ci vediamo noi mercoledì prossimo e dalla prossima settimana faremo lezione anche il venerdì dalle 9 alle 11, ok?
Va bene.
Va bene.
Va bene.
Arrivederci.
Allora, buon 1° maggio e buon weekend. Arrivederci.
Arrivederci, grazie.